Hi, I'm Steven, and I will be starting our group's presentation, and our project was a Rubik's Cube solver. The goal of our group's senior project is to build and program a mechanical setup that can manipulate and solve a 3x3 Rubik's Cube in 5 minutes or less, and to act as an exhibit piece for our major at student recruiting events. It is also meant to display some of the skills we learned here in the ESET program, such as 3D CAD drawings in SolidWorks, electrical circuitry, and programming. We also had optional features planned that we would add if time permitted, such as an automated randomized cube scramble where the machine would randomize the cube for it to solve. We also thought it would be cool to connect a tablet and program a GUI that would display code as it is running and be able to send commands to the machine by touching the screen. Why this design? From the start, we wanted to find a project that would be interesting to watch in action. While there are simpler Rubik's Cube solvers out there, we decided to use the design we found on Instructables.com called ARS Arduino Rubik's Solver, posted by Super Mario Professor. The main reason we chose this design is most of the structures are made of acrylic, and there are many mechanical moving parts which would make it interesting to watch as it solves the cube. This project also had some documentation available online, such as the files needed to cut the acrylic pieces readily available, a collection of some of the algorithm code that would be used, and a list of materials needed. The drawbacks of this design is the original project was made at a university in Italy, so the instructions were mainly in Italian and it was difficult to understand and translate. Another is that the pieces are made out of laser cut acrylic, so it's going to cost more in financing than other designs. And also because of all the moving parts, we're going to have to spend more time on testing. While we did have the laser cutting files, we had to make all of the engineering drawings and 3D models ourselves. We used SolidWorks CAD software to make the drawings and models, and we also made assembly files to check for clearances and to make sure everything would fit together as intended. In total, we had 29 individual acrylic pieces to model. We also used SolidWorks to redesign the mount for the camera. For the assembly of our project, we had a custom stained and scored baseboard, 100 individual acrylic pieces, custom fabricated metal rods with tapped ends, 3D printed pieces for the mechanical belts, cube manipulators, and camera mount, and it took about 40 hours to assemble all together. The biggest delay we found was that the acrylic used in the original project was in metric thicknesses, and to get those type of thicknesses in the US would be a significant increase in cost. We decided to alter the design to fit imperial thicknesses that is readily available at places such as Home Depot. This slowed down productivity because each piece needed to be altered in SolidWorks and checked for accuracy. This redesign delayed the project 2 weeks. Once the CAD files were changed and the acrylic sheets had arrived, we had the acrylic laser cut at a local shop. It took about a week turnaround. Once we started to put everything together, we found out that there were missing pieces and had to make a second order for laser cutting. During the second order, there was a mistake in one of the files where the units had changed from centimeters to inches and caused a dimension problem for the cut piece. The lesson learned is to always check units before sending files for fabrication. The top piece in the picture to the right is the correct size. The Sharpie pen is for scale. In our project, there are 4 8x572mm shafts that hold up the motor structures that manipulate the cube. The problem we ran into with these rods is they are tapped at the end so they can be held in place. Turns out that buying custom shafts with tapped ends is very costly. Luckily, Julian is an experienced metal fabricator and had access to a metal lathe to tap the ends, but this added a few weeks delay for construction. We had to modify the design a few times as we were putting it together. For all the sliding motor chassis, we found that they were unstable with just a force fit. We ended up using some extra acrylic as washers and drilled out holes for screws. This solidified the chassis and solved our problem. Another modification we had to make to our original design was to the 3D printed cube grippers. The opening was too small to slide onto the shafts of the motors, so we drilled out the gripper and added a set screw to the side to hold it in place. Also, in the original design, it called for fans for the motors that rotate the cube, but we had to omit them. The reason being is the motors that we used were longer than the ones used in the original design, and the fans would not fit in the space behind the motor. We also had to modify the motor box housing. The motors we used had a little lip that sticks out just enough to keep the motor box roof from fitting all the way into place, so we drilled out an opening in the roof using a Dremel tool.